Hello, welcome to another exciting class in physics. I am Wizard Gift. Our topic today is simple harmonic motion, part 3. For a motion to be simple harmonic, its acceleration must be directed towards the equilibrium position. In today's class, we'll be focusing on the acceleration of a simple harmonic motion. Let's go on to see our lesson objectives. By the end of this class, you should be able to show the relationship between linear acceleration and angular velocity. You should also be able to show the relationship between linear and angular acceleration. In our previous lessons, we've been able to define simple harmonic motion, explain some terms associated with simple harmonic motion, relate simple harmonic motion to circular motion, and also show the relationship between linear and angular velocity. In this class, we'll be focusing on linear and angular velocity of a simple harmonic motion. Before then, let's take a quick comparison of linear velocity and angular velocity as treated in our previous class. Linear velocity is the rate at which linear displacement changes with time, while angular velocity is the rate at which angular displacement changes with time. Linear velocity is measured in meters per second, while angular velocity is measured in radians per second. Linear velocity v is mathematically represented as v equal to x over t, while angular velocity is represented as omega equal to theta over t. And lastly, linear velocity relates with angular velocity by the formula v equal to a omega, where a is the amplitude of the motion, while angular velocity relates with linear velocity by the formula omega equal to v over a, where a is the amplitude of the motion. In our previous class, we were able to show the relationship between linear velocity and angular velocity by considering the motion of a particle along a circular path. We can also show the relationship between linear acceleration and angular velocity by considering the same circular motion. Recall that from the part 1 of this topic, we define linear acceleration as the rate at which linear velocity changes with time. We also noted that it is measured in meters per second squared. Mathematically, linear acceleration A is equal to change in linear velocity over time. This can also be written as A equal to Vt minus Vo over t, where Vt indicates the final velocity and Vo indicates the initial velocity. Now consider this diagram carefully. By trigonometric identities, cos theta is equal to adjacent over hypotenuse. And our adjacent here is S, while our hypotenuse is A. That means cos theta is equal to x over A. When we make S the subject of the relation, we have x equal to A cos theta, where A is the amplitude of the motion. Since this motion is a circular motion, its acceleration is centripetal. And centripetal acceleration is given by the formula A equal to minus v squared over r. Since the radius r is equal to the amplitude of the motion, A is equal to minus v squared over capital letter A for amplitude. Recall that from our previous class, we saw that v is equal to omega A, where v is the linear velocity, omega is the angular velocity, and A is the amplitude of the motion. Substituting omega A for v into this equation, we have A is equal to minus omega A all squared over A. This gives us minus omega squared A squared over A. This A cancels one A at the top here. We are left with minus omega squared A. Hence, acceleration, small letter a, is equal to minus omega squared A. Now, the component of this acceleration on the x direction is A equal to minus omega squared A cos theta. But we've been able to establish that x is equal to A cos theta. Therefore, substituting x for A cos theta in this equation, we have A is equal to minus omega squared x. Therefore, the equation that relates linear acceleration with angular velocity is A equal to minus omega squared x. And at maximum displacement, s is equal to A. Therefore, at maximum displacement, A will be equal to minus omega squared A. Having established that relationship, let's go on to solve some examples. Example 1. A body in simple harmonic motion makes 50 cycles in 5 seconds. If the amplitude of the motion is 5 meters, find the linear acceleration at A, the midpoint, B, the maximum displacement. Now from the question, the number of cycles n is 50 cycles. Recall from the part 1 of this lesson, we established that when n is equal to 1 cycle, theta is equal to 2 pi radians. Therefore, when n is equal to 50 cycles, then theta will be 50 times 2 pi, which gives us 100 pi radians. Also from the equation, the time taken to complete the 50 cycles, small letter t is equal to 5 seconds. And our amplitude of the motion A is equal to 5 meters. We are asked to calculate the linear acceleration. The formula for calculating the linear acceleration, considering the parameters given, will be A equal to minus omega square x. But angular velocity omega was not given in the question. However, we can easily calculate it using the formula omega equal to theta over t. Our theta is given as 100 radians, and our t is given as t equal to 5 seconds. So substituting 100 pi for theta and 5 for t, we have 100 pi over 5. This gives us 20 pi radians per second. So far, we've been able to establish that angular velocity omega is equal to 20 pi radians per second. Now we have to calculate the linear acceleration at midpoint. The midpoint is also called the equilibrium position, and at the midpoint, x is equal to 0. That means there is no displacement. So substituting 0 for x in this equation, we have a is equal to minus 20 pi squared times 0. This gives us 0. So our acceleration at midpoint is 0. The next we have to look for is the linear acceleration at maximum displacement. At maximum displacement, s is equal to the amplitude of the motion, and we are given the amplitude as 5 meters. So substituting 20 pi radians for omega and 5 meters for x, we have a equal to minus 20 pi squared times 5. Minus 20 pi all squared gives us minus 400 pi squared. Going further, we multiply by 5, which gives us minus 2000 pi squared. Now remember that the negative sign shows the direction of the acceleration. Therefore, the magnitude of the acceleration is A equal to 2000 pi squared meters per second squared. Generally, in a simple harmonic motion, linear acceleration is minimum at minimum displacement and maximum at maximum displacement. Now let's go on to solve another example. A horizontally mounted wheel moves with a frequency of 20 Hz. If its radius is 5 meters, find its A, angular speed, B, linear acceleration. From our question, frequency f is equal to 20 Hz, and the radius of the motion is 5 meters. Remember that radius gives us the amplitude of the motion, so our amplitude A is also equal to 5 meters. We have to calculate the angular speed and linear acceleration. From the parameters given to us, angular speed can be calculated using 2 pi f, since we know the frequency. Our frequency is given as 20 Hz. When we substitute 20 for f in this expression, we have omega is equal to 2 times pi times 20. This gives us 40 pi radians per second. Next, we have to solve for linear acceleration. Since the radius of the motion is given and we've calculated the angular velocity to be 40 pi radian per second, the linear acceleration can be calculated using the formula A equal to minus omega square x. Substituting 40 pi for omega and 5 for x, we have A equal to minus 40 pi all squared times 5. This is the same thing as minus 40 square pi squared times 5. 40 squared gives us 1600. Therefore, we have minus 1600 pi squared times 5. This gives us minus 8000 pi squared meters per second squared. And the magnitude will be 8000 pi squared meter per second squared. So far, we've established a relationship between linear acceleration and angular velocity. Let's go on to show the relationship between linear acceleration and angular acceleration. Mathematically, linear acceleration A is equal to change in linear velocity over time, which can be written as A equal to V over T. Linear acceleration is measured in meters per second squared. On the other hand, angular acceleration alpha is equal to change in angular velocity over time, which can be written as alpha equal to omega over T. Recall that omega denotes angular velocity. Angular acceleration is measured in radians per second squared. From our previous lesson, we established that V is equal to R omega, where V is the linear velocity, R is the radius, and omega is the angular velocity. Making omega the subject, we have omega is equal to V over R. Now substituting V over R for omega into this equation, alpha equal to omega over T, we have alpha is equal to V over R over T. By simplification, alpha is equal to V over R times 1 over T. Now, since R times T is the same thing as T times R, we can rewrite this equation to be alpha equal to V over T times 1 over R. But our acceleration A is equal to V over T, that is velocity over time. Therefore, substituting A for V over T in this equation, we have alpha is equal to A times 1 over R, which gives us alpha equal to A over R. When we make A the subject of the formula, we have A is equal to R alpha. But remember that our radius R is the same thing as the amplitude of the motion. Therefore, this can be written as A equal to capital letter A for amplitude times alpha. Now, having established that relationship, let's go on to compare linear acceleration with angular acceleration. First, linear acceleration is the rate at which linear velocity changes with time, and it is denoted by A, while angular acceleration is the rate at which angular velocity changes with time, and it is denoted by alpha. Mathematically, linear velocity A is equal to Vt minus Vo over T, while mathematically, angular acceleration alpha is equal to omega T minus omega O over T. Next, linear acceleration is measured in meters per second squared, while angular acceleration is measured in radians per second squared. Linear acceleration relates with angular acceleration by the formula A equal to R alpha, while angular acceleration relates with linear acceleration by the formula alpha equal to A over R. Having looked at those differences, let's go on to solve an example. If a merry-go-round of radius 2 meters makes 8 revolutions per second, calculate its linear acceleration and angular acceleration at maximum displacement. From the question, our radius is equal to 2 meters, which means our amplitude A is equal to 2 meters. And the frequency of the motion is given as 8 cycles per second. Remember that another word for cycle is revolution. So our frequency F is equal to 8 cycles per second, or 8 Hz. We have to calculate the linear acceleration A and angular acceleration alpha. Now, for linear acceleration A, we use the formula A equal to minus omega square x. Angular velocity was not given in the question, but we can easily calculate it using the formula omega equal to 2 pi f. Since our frequency F is equal to 8, we have omega is equal to 2 times pi times 8. This gives us 16 pi radians per second. At maximum displacement, x is equal to the amplitude of the motion, that is, s is equal to a. So our linear acceleration can be calculated using the formula A is equal to minus omega square A. So, but we've calculated our omega to be 16 pi, and our A was given to be 2 meters. That means substituting 16 pi radians per second for omega and 2 meters for amplitude A, we have A is equal to minus 16 pi all squared times 2. This gives us A equal to minus 256 pi squared times 2, which further gives us A equal to minus 512 pi square meters per second squared. Now the amplitude of this acceleration is A equal to 502 pi square meters per second squared. Finally, to solve for the angular acceleration, we use alpha equal to A over R, where R is the amplitude of the motion. So substituting 512 pi squared for acceleration A and 2 for radius R, we have alpha is equal to 512 pi squared over 2. This gives us 256 pi square radians per second squared. Having solved that example, we've come to the end of this class. But before we go, let's take a quick recap of all we've learned so far. First, we learned that linear acceleration is the rate of change of linear velocity with time. Next, we learned that angular acceleration is the rate of change of angular velocity with time. Going on, we learned that linear acceleration A equals the product of the angular acceleration alpha and the radius r. Therefore, A is equal to r alpha. Finally, we learned that linear acceleration can be related to angular velocity with the formula A equal to minus omega square x. Now let's try out some test questions. Question 1. Which of the following is not true of linear acceleration? A. It is the rate of change of linear velocity with time. B. It is equal to the product of the angular acceleration and radius. C. In a simple harmonic motion, acceleration is in opposite direction as the displacement. D. Acceleration is equal to the product of the angular velocity and the amplitude of the motion. The correct answer is option D. Question 2. An object moves along a circular path of radius 1.5 meters. If its angular acceleration is 6 pi square radians per second squared, find its linear acceleration. The correct answer is option B, 9 pi square meter per second squared. Thank you for your time. Till I see you again in another interesting physics class. Bye-bye.